Okay, so let's continue. So we finished talking about the logistic regression. So this is the second machine learning method we covered. So the first one is continuous neighbor, and second is logistic regression. And next we are going to base on the Bayesian classifier to introduce the third type of method, LDA and QDA. And first of all, let me review the Bayesian classifier. So the Bayesian classifier is defined as the mapping from X to a possible class belonging to a set including capital K different classes, such that the minimum risk can be obtained. And so within such a framework, so the zero and the one loss function is used. And it can be shown with some mathematics that the Bayesian classifier will be the largest conditional probability that Y belong to the case class, given that given X. Okay. Okay, so now suppose that we assume that X here is continuous. So the density here, we should use F. The density of X can be written as a mixture of K classes. Okay, so the density function itself, Fx, can be written as the probability of X smaller or equal to X. Okay, this is the definition about the density function. So it can be written as the sum over all the possible classes, and then multiplied by the prior probability that Y belong to the case class. Okay, so K ranges from 1 to capital K, and then we have the conditional density function, which is capital X smaller or equal to X, conditional that Y belong to the case class. Okay, so the first part is the probability of Y belong to the case class. We don't have any information from the data, so we may call this to be the prior probability for class K. So we use the pi k to denote as the prior probability. And we denote the second part as the fk of x, denote as, given that Y belong to the case class, what is the density function for capital X? Okay. So this is just the total formula, the formula of total probability, okay? So then by the Bayes theorem, so actually our target is to estimate the probability Y belong to the case class, given that X equal to small x, okay? So if X is a continuous random variable, we may set capital X smaller or equal to small x, okay? And then by the Bayes formula, okay, so this should be equals to the probability of Y belong to the case class and X, capital X smaller or equal to small x. And then divided by the probability of capital X smaller or equal to small x. This is just the density function of X, okay? You have the formula here, okay? And for the top part, okay, so we can get a further representation that is actually the probability Y belong to the case class multiplied by the conditional probability. That is the probability that capital X smaller or equal to small x, conditional that Y belong to the case class. Okay, so then the first part will be the pi k, and the second part is just fk of x. Okay. So you can see that our target is to find K such that the conditional probability is maximized. And by using the Bayes theorem, we can equivalently represent in the following form. You can find that pi k times fk of x, that's in the numerator, and on the denominator, that is pi k times fk of x, and the sum over all the possible classes. And remember here, we want to find K such that the conditional probability is maximized. But on the equivalent representation, on the denominator, you sum all the possible classes. So the denominator will be a constant with respect to K. So in a sense, if we want to find K such that the conditional is maximized on the left-hand side, it is equivalent to find that pi k times fk of x, if we can find k such that this product is maximized. So these are actually equivalent because the denominator is a constant with respect to k. So sum over all the possible value of k. Okay. So this pi k times fk of x are called the discriminant function. So this derivation will suggest us, in order to maximize the conditional probability, it is equivalent to maximize a pi k times fk of x. So if we can know the formula for yk and fk of x under some parametric model assumption, then we can easily calculate the conditional probability and find the maximum value. Okay, so let me give you one example. And so under the normal assumption, and this is actually a one-dimensional problem. Okay, so suppose that there are two classes and the two classification problem. So we have class 1, class 2, and assume that so x belongs to the normal distribution with mu y and the constant variance. Okay, so y here can be taken the value of capital Y can take the value of y 1 or 2, corresponding to two different colors, in either the purple color or the green color. Okay, so in that sense, and with the equal prior probability, that means pi 1 will be equal to pi 2 equal to 50%. Okay, so if y is so if y is 1, correspond to the left curve, the green curve. If y is 2, correspond to the purple curve. So if y belongs to the so if y is 1, then x will follows from a normal distribution with mu 1 and a sigma square. If y is 2, then x will follow from the normal distribution with mu 2 and a sigma square. While mu 1 is -1 and mu 2 is +1. Okay, and now because of pi 1 and pi 2, these are actually the same prior probability. And remember, we want to find the class such that the pi k times fk of x, the density function, will be maximized. Okay, so this is the density function for the first class, and this is the density function for the second class. And we know that pi 1 and pi 2 are the same. So then if you want to choose which of the product is larger, then you just compare which density is larger in different areas. Now you can see that, okay, so in the middle area, so f1 of x is the same as f2x. Okay, so meaning that this is a decision boundary. So meaning that here, the 0x equal to 0 will be the decision boundary. Okay, so on the left, so f1x correspond to the blue curve, and the f2 of x correspond to the purple curve. So the blue curve, the density function will be larger than the purple curve. So for that means for x smaller than 0, we may classify those points to be green. Okay. So on the right-hand side, so density function for the purple curve is be larger than the density function for the green curve. So that means actually we may need to, for the points x larger than 0, we may classify those points to be the purple class. Okay, so that's the first setting. And the second setting, everything is the same, but the only difference is the prior information is different in terms of the prior probability. So pi 1 will be 0.3 and pi 2 will be 0.7. And then if you calculate pi 1 f1 of x, oh, sorry. So if you calculate pi 1 of f1 of x and pi 2 of f2 of x, it will just give you two curves. Okay, so you can see that in the dashed line here, so pi 1 of pi 1 times f1x is the same as pi 2 times f2x. So meaning that the decision boundary is here. So x will be slightly smaller than 0. Okay, so on the left-hand side, so pi 2 f2x is larger than pi 1 f1x. So for these points, we may classify the points belong to the green class. on the right, so pi1 times f1x is larger. So we may classify those points belonging to the purple class. Okay, so this is actually illustration about how we can make our further classification assignment. That is actually we just calculate the pi k times fk of x. Okay, so for all the possible class, k ranges from 1 up to capital K. Okay, so in practice, so pi k and fk of x are unknown. Okay, so even if under this simple example, we assume that x follow from the normal distribution, but this normal distribution is parametrized by the two tuning parameter, which is mu y and sigma square. In order to estimate, so we need to actually estimate those parameters from the data. So in this particular example, we need to estimate pi1, pi2, mu1, mu2, and the sigma square. So there are 5 parameters that I want to estimate. Okay, so these parameters need to be estimated from the training data. Okay, so to move further, as we consider, so everything is under the normal assumption, normality assumption. Okay, suppose that we have a capital K different classes. Okay, so for each small k, that capital Y belong to the case class, we assume that x follows from the normal distribution with mean equal to mu k and variance equal to sigma k square. And now we assume that the sigma k will be the same across different class, meaning that the sigma k will be a constant equal to k across a different value of k. Okay, so if this is the normal distribution, then we can easily write down the density function like the follows. Okay, so this is a standard deviation, and this is the mean. Okay. Okay, and by the previous derivation, we may need to calculate, for example, conditional probability. So it will be proportional to the prior probability times the density function. Okay, so we know this is a prior probability, and this is a density function by assuming that y belongs to the case class, the density function for x. And in the denominator, and this is a constant with respect to k, so we will not consider the denominator. Okay, so then in order to make a further classification assignment, we need to actually compare the magnitude of the numerator for different value of k. Okay, so we need to actually assign x to the class with the largest discriminant score, which is just the value on the numerator. Okay, and this is a exponential function. To facilitate the further computing, we may take the log transformation, and because the log transformation is a monotone function, this will not change the relative magnitude. Okay, if we take the log transformation, the first part will just become the log of pi k, and the second part will become like 1 minus, okay, 2 square, sigma square, and then x squared minus 2 times x times mu k plus mu k squared. Okay, so we need to actually calculate this value for different value of k. So we can just remove those terms that are not depending on k. Okay, so the first term depends on k, so we have the first term. Okay, so that is the first term still remains. And for the second term, minus x squared divided by 2 times sigma squared. So it's a constant over k, so we can just ignore this term. And for the third term, it is 2 times x times mu k divided by 2 times the sigma squared. It's also a function of k, so it varies with respect to k. So that term should also appear. And that term will just become the first term here. That is x times mu k divided by sigma squared. And the last term is minus mu k squared divided by 2 times sigma squared. It's also a function of k, so we still keep it. That becomes the second part. Okay, so that means actually for each value of k, we can just calculate this delta function and choose the value So for example, if for capital K equal to 3, we may calculate delta 1x, delta 2x, and delta 3 of x. And we may choose the one with the largest delta function, and then we can make our classification assignment. Okay, so here, this is a question. So if we consider two-class classification problem, and pi 1 equals to pi k equals to 20%, so what is the Bayesian decision boundary? Okay, so now in this scenario, so pi k will be the same. So the last part will be canceled out. So you don't need to consider last part. And you only consider pi 1 and so mu1 and mu2. And because we said sigma is the same. And if we consider Bayesian decision boundary, we need to guarantee that so delta 1x should be equal to delta 2x. Okay, so this is equivalent to x times mu1 divided by sigma square minus mu1 square divided by 2 times sigma square should be equal to delta 2x, which is x times mu2 divided by sigma square minus mu2 square divided by 2 times the sigma square. And then by some further calculation, you can show that in order to make delta 1x equal to delta 2x, x should be equal to mu1 plus mu2 divided by 2. Okay, so this will correspond to the Bayesian decision boundary in the sense like our conditional probability for the class 1 and the class 2 will be the same. Okay, so this will correspond to the decision boundary. Okay, so this also verify our previous example, because in the previous example, mu1 is -2 and mu2 is +2. So -2 plus +2 divided by 2 will just be 0 if pi 1 and pi 2 are the same. Okay. Okay, so those are actually the result under the population level if we know pi 1, pi 2, mu1, mu2, and a sigma square. Of course, in the real data scenario, we don't know how the data are generated, okay? So we need to actually estimate the underlying parameters. So including, so for example, if we consider the two-class classification problem, we may have pi 1, pi 2, f1 of x, f2 of x, and within f1 of x, f2 of x here, it depends on the mu1 and the sigma square, and the mu2 and the sigma square. So there are 5 parameters we want to estimate, okay? And from the data, you can see that the density function, so f1 of x, we don't know it in practice. And because this is a simulation data set, so we want to actually generate our simulated data according to some known distribution. Okay, so we know what's the form for f1 of x and f2 of x. And then we generated data. And based on the data, we can plot the histogram. Okay, so plot the histogram. So this histogram program can be thought as approximation for the true density function of f1 of x. And this pink part corresponds to the histogram belonging to the pink class. And this will correspond to the approximation or the estimate of the f2 of x. Okay. And for these two histogram, you can see that the estimated decision boundary is the black dashed line. And the true decision boundary, which is the Bayesian decision boundary, is the black solid line. Okay, so they are actually quite close. So the black solid line and the black dashed line are quite close, meaning that, okay, so the estimated decision boundary is quite similar to the true decision boundary. And this is very intuitive because we know how the data are generated. And we know that the data are generated according to the normal distribution with the two possible classes. The first class is f1 of x, and the second class is f2 of x. And if the data are generated according to the normal distribution, of course, if we estimate the data by the so-called linear discriminant analysis under the normality assumption, then our estimated decision boundary will be quite close to the true decision boundary. Okay, so I forgot to talk about why we call our approach the linear discriminant analysis. Okay, so let's move on to the previous page. Okay, so remember here in the previous page, there is a key assumption that is actually this sigma square is the same across different class. Okay, so if this sigma square, this sigma is different across different class, then you may need to include here like a sigma k here and a sigma k here. Okay, and also you also need to consider the quadratic term. Like remember, in the previous setting, if sigma k is the same across different k, then sigma square divided by 2 times sigma square, this will be a constant with respect to k. But if we do not have this assumption, then this sigma k will also depend on k. From that perspective, if so we need to actually also include the quadratic part. That is actually the minus x squared divided by 2 times sigma k squared, okay? And then we want to compare the value of different delta k. But in this setting, the quadratic form also appear. That actually will make the decision boundary to be quadratic. But now, if you assume that this sigma k is the same across different k, this term will not be considered. Now the decision boundary will just be linear. So that's the reason why we call this approach to be the linear discriminant analysis. If we have the assumption that the variance term will be the same across different class. If we do not have this assumption, then we will include additional quadratic term that will correspond to the quadratic discriminant analysis to be discussed later. Okay, so in order to estimate the parameters, so here this part is not required, but here we provide a formula to estimate those parameters. Okay, we just give some intuitive explanation, and this part of derivation is not required. Of course, if you want to practice more, you can derive everything by yourself. So you can just use the maximum likelihood estimator, okay, trying to write down the likelihood function and solve, maximize the likelihood function, okay? So pi1k, pi k hat equals nk divided by k, divided by n. N here is actually the total number of observations, while nk is actually the number of observations belonging to the case class. Okay, so this is a very natural result because this just measures the proportion of the observations belonging to the case class. So this can be considered as the estimate of pi k. Okay, so similarly for mu k, we can give the estimate for mu k. We call it mu k hat. This is an estimate for mu k. Okay, so so that is actually for all the observations belonging to the case class. So for the audio, that is actually for all the I, well, yi equals to k, that means for all the observation belonging to the case class, we take the sample average of the x here. Because the total number is nk, because belonging to the case class, we have nk different observations. And for those observations, we take their sample average. And then this will give the estimate of mu k, okay? So finally, we may give the overall estimated variance, okay? So that is the follows, okay? So remember, first of all, let's consider the first part inside, okay? So you can see that you sum over I, well, yi belong to the case class, okay? So this is actually just the sample variance for the observations belong to the case class. And this is the sample mean for the observations belong to the case class, okay? Remember, this is just the formula to calculate the sample variance for those observations belonging to the case class. And finally, because we assume that sigma 1 equal to sigma 2, while the variance is the same. So actually, this is actually the estimated variance for the case class. We need to pull over the estimated variance across different class and finally give an overall estimate for the variance. So to do that, we need to sum over all the possible class. And here, this term is the estimated variance. And finally, we need to divide it by the degree of freedom. Okay. So remember, here we need to divide it by n minus k. That is intuitive because in total we have n observations, and in order to estimate so actually k parameters has already been estimated because we need to estimate mu1 up to mu k. So these are the parameters that are already been estimated. So the effective degree of freedom will just be the number of observations minus the unknown parameter that has already been estimated. So the effective degree of freedom will just be n minus k. Okay. So it can also be represented as the weighted sum over the sample variance across different class. So this is the sample variance for the case class, and we sum over all the possible class. And here, this is the relative weight. Okay. Okay, so you don't need to know how to derive this result, but you need to actually to have the general intuition why we have this result and why the result makes sense. Okay. Okay, so we are already talking about the univariate setting. That is in the case like p equal to 1. Okay, so we may assume that the data set, the x is a one-dimensional variable follows from the univariate normal distribution. So in the setting that the p is larger than 1, this will correspond to the multivariate normal distribution, which can be thought as the multivariate extension of the univariate normal distribution to the multivariate setting. Okay. So the formula is the same, but we just need to give a new definition about the density function for the multinormal distribution. Okay. Okay. Suppose that y belongs to the case class, and x here is just a p-dimensional, including x1, x2, etc., xp. So a p-dimensional vector. Okay. So this x will follow from the multinomial distribution with mean vector equal to mu k. So that actually still be a vector including mu k1, etc. up to mu kp, p-dimensional vector. Well, also we have the covariance matrix. So this covariance matrix is a p by p matrix. Okay. So for example, this covariance matrix can be written as sigma 1, 1, sigma 1, 2, etc., sigma 2, 1. So this is a symmetric matrix. And also positive semi-definite. Okay, so for example, for sigma jk, so it is just the covariance of xj and xk. Okay, so now I consider everything under the conditional setting. So so these are actually just the result under the conditional setting. Okay, so this is a p by p matrix. So first of all, why is symmetric? Because actually you can switch the order of xj and xk, and you can show that this matrix is symmetric. And I will leave you as a homework to showing you that this p by p covariance matrix is also positive semi-definite. Okay, please show it. And so actually there's a very simple approach to show this result. And this can be a possible interview question for a financial company. Because this will have a very nice connection with some portfolio optimization problems. Okay? And for this type of very normal distribution, we can write down the density function. So given that y belongs to the case class, okay, so we may have this representation. Okay, so this means the inverse of the covariance matrix. Okay, so this is p by p, and x here is p by 1, mu k is p by 1, so this part p by 1. And the first part, if you take the transpose, so that will be 1 by p. So the whole part will just be a scalar, okay? And here, sigma here is actually the p by p matrix, and we take the determinant and take the square root of that. And finally, we need to multiply by the constant. Remember, when p is 1, then this part will be root 2 pi, the same as the density function for the standard normal for the normal distribution. Okay, and if p is 1, then this sigma will just be sigma squared. And if you take the square root, then this part will be sigma, still the same as the density function for the univariate normal distribution. And by some mathematics, you can show that if p is 1, then this result will be reduced to the density function for the univariate normal distribution. Okay, so now we need to actually follow the same procedure, okay, by taking the log of the density function and then multiply by by taking the log of pi k times fk, okay, and then we remove the terms that do not depend on k. Okay, so here we'll make an assumption that so sigma 1 equals to sigma 2, etc. equal to sigma capital K. So these are actually the covariance matrix for the case class. And remember, in the univariate setting, we assume the same covariance, same variance. And under the multivariate setting, we may assume the same covariance matrix across the different class. We may assume sigma 1 equal to sigma 2, etc. equal to sigma. Okay, so by the similar derivation, we will also remove the quadratic term, which is x transpose times sigma inverse times x, okay? And because this term will not depend on k, so this term can be removed, okay? And if you take the log transformation, the log pi k will be remained. And we also have some linear term in term with respect to x, okay? So because here, x transpose sigma inverse times minus mu k, sorry. Okay, so that's the take the log of that part. That will be minus 1/2 x transpose sigma inverse mu k, and because you have minus and minus, so it will be positive. Okay, so and if you take the mu k here and the x here, you may have the second term. So so this is negative and this is negative. So the overall effect will be positive. So you still have the second part, which is second linear part, which is 1/2 times mu k transpose times sigma inverse times x. And then you have the remaining part correspond to the quadratic form of mu k. That is actually minus 1/2. So mu k transpose sigma inverse and mu k. And then lastly, you have the log of pi k. And then you can just find that the first two terms are the same. Okay, the two first terms are the same. Why is that? Because this one is just, you can treat this term as, for example, a vector of A, and this term as a vector of B. So we should know that the transpose, so the transpose of A times B should be the same as the transpose of B times A. Okay, so so you can switch the order. Okay, so you treat X to be A, and sigma inverse times mu k to be B. And by using this formula, then you have sigma inverse mu k, and then transverse times x should be the same as should be the same. Okay, so now you treat x to be A and the sigma inverse mu k to be B, and then you apply this formula. Okay, then you can find that the first two terms are the same because sigma here is a symmetric, so sigma inverse is also symmetric. So the inverse, if you consider transpose, it will be the same as the inverse itself. Okay. Okay, so I'm not going to discuss the derive the further mathematical details, but actually you can see that we just rely on the delta function as follows. Okay, so again, we don't have the quadratic term. So we may need to make the delta k, for example, if I have two class, we may need to assume that the delta 1 of x the same as delta 2 of x. And then we can solve that, solve the decision boundary such that delta 1x equal to delta 2x. And then we can give the decision boundary, which is the Bayesian decision boundary. Okay. And from the data, you can estimate the parameters. Here, there are many parameters. There are parameters mu1 up to mu k, and also parameter of this p by p matrix. So this will be a very high dimensional problem if p is very large. Because for sigma here, there will be p times p plus 1 divided by 2 parameter we want to estimate. Here, we need to have the assumption that we need to use the result that this sigma is symmetric. Okay, so let me give you an example, and this is a 3-class classification problem, and this is still a simulation data, so we know how the data are generated. Okay, so so if we know how the data are generated, we can easily calculate the Bayesian decision boundary. And of course, we have a 3-class. And here, the dimensionality for the problem will just be 2, because we have actually 2 variables. And the capital K will be 3, okay? So on the left-hand side, this will show us the Bayesian decision boundary and how what is the true density function for this multivariate normal distribution, okay? So you can easily calculate the density function. For example, also you can calculate the delta 1 of x, delta 2 of x, and the delta of 3 of x. Okay, and so you can see that on the boundary part, so the delta function for the yellow and the blue should be the same. And this part, the delta function for the orange will be larger than the delta function for the blue. And also this part, the delta function for the orange will be larger than the delta function of blue here, okay? So you can consider the part will give the largest delta function for orange, and this part gives the largest delta function for green, and this part gives us the largest delta function for blue, okay? And now we simulate our data, we generate our data, and by applying the LDA, then you can give an estimated decision boundary. Okay, so you can see that the estimated decision boundary is quite similar as the true decision boundary, which is the Bayesian decision boundary. And then we can calculate the Bayesian error rate. Remember, in the Bayesian error rate is the error rate that you can never achieve a lower value than that, because this is around like 7.46%. Okay, but if you're using the LDA approach, you get a relatively larger error rate. And this is reasonable because the Bayesian error rate is the minimum error rate you can achieve. And these error rates are quite similar. That's also reasonable because we know the data are generated from the multivariate normal distribution. And if you are using the LDA approach, the basic assumption is that we assume that the data follows from the multivariate normal distribution. Okay, so we know the data generated from the multi-normal distribution, and we estimated the model, estimated parameter under the same multivariate normal distribution assumption. Therefore, we get a very good estimation in terms. So here you can see that the error rate by the Bayesian, so in terms of the Bayesian error rate and the LDA error rate, they are quite similar. Okay. And in terms of the parameters of interest, we need to, in order to characterize the multivariate normal distribution, we need to actually estimate the mean function and the covariance matrix. Okay, so of course the prior distribution. So we have hat on top of that to denote this is the estimated value from the data. Okay, and this is actually the same as the one-dimensional case, and this is also the same as the one-dimensional case. And the last one is actually the weighted sample covariance estimation. Okay, so if you consider the inside part, that is actually the sample covariance matrix for the observations belonging to the case class. Okay, so this is the sample mean belonging to the case class. Okay, so this will be p by 1, and if you consider the transpose, that will be 1 by p, and their product will be p by p, and this will be estimated covariance for those observations belonging to the case class. And then finally, we sum over all the possible value of k and divide it by total effective degree of freedom. So this will give the overall estimate for the sample covariance matrix. Okay. Okay, so that's it. That's the end of this part.